get started. Okay, so last time we discussed essentially the basics of vector spaces, linear transformations, and all of this was done in a pretty shady way, I admit, but hopefully y'all were able to gain some sort of understanding about what I was trying to talk about with these vector spaces and linear transformations. And then more rigorously, we were able to talk about matrices representing linear transformations. And this was done by viewing an n by n matrix, or actually maybe an n by m matrix, and viewing a vector as a n by 1 matrix, right? So in this picture, here I have an n by m matrix, n by m, and then here I have some m by 1 matrix. So here's a linear linear transformation. And here is a vector. It's also a matrix, but we think of this as a vector. And then this will give out a matrix, which is going to be an n by 1 matrix, which is another vector. And the rule is that how do we get this new vector from these two matrices, or this matrix and this linear transform and this vector? We do matrix multiplication via matrix multiplication. So after yesterday, are we generally okay with this picture or this way of understanding things? Yes? No? Any questions here? Yeah, this is okay? Okay. The next thing that we wanted to talk about is we asked about when is a matrix invertible? An n by n matrix invertible. First of all, can someone remind me what it means for a matrix A to be invertible? What's the definition?
Find another matrix such that when you multiply them, you get the identity matrix.
Exactly. A invertible is equivalent to there existing a matrix B such that A times B is equal to ID, the identity matrix. Okay. We all right with this? And here we're talking now strictly within n by n matrices. And then we have a check. How do we check whether a matrix is invertible or not?
You look for a non-zero determinant.
Yes. Inverta or invertee? Invertibility?
Yeah.
I don't know if that's an I or an A. It's an I? Okay, great. How do we check invertibility? Determinant being non-zero. And then we also discussed how to compute determinants, and it's by cofactor expansion. Practically in this class, we'll probably only ever do 2x2 determinants, which you already know, or 3x3 determinants, which you also already know. Maybe at some points, and yesterday I briefly discussed a 4x4 determinant. Right. Okay, any questions on this material, which is my brief summary of what we did yesterday? You okay with this? Okay, there's more to be said in terms of matrix manipulations, but what I want to do now is move on to systems of linear algebraic equations. This is essentially a companion chapter to 7.2. It's still all linear algebra and no differential equations, more or less. Okay. So what we're going to write is the following. A system of linear algebraic equations looks exactly as follows. A11 of x1 plus A12 of x2 all the way up to plus A1n of xn is equal to B1, all the way down through an1 of x1 plus an2 of x2, all the way up through ann of xn is going to be equal to bn. Right? This is something that is familiar to you from some long time ago when you learned how to solve these linear equations either by elimination of variables, otherwise known as Gaussian elimination, or substitution methods. So these things at least are familiar to you from the pre-calculus days. Not pre-calculus, but before calculus. And what we want to write here, a concise way of expressing this equality, is the following. This is ax plus, or is equal to b, where A is equal to the matrix given by Aij, x is equal to the vector x1 all the way up through xn, and b is equal to the vector b1 all the way up through bn. Right? We see that if I write A as this matrix, and then I do the matrix multiplication A times x, then I will essentially produce something that looks exactly like this for my vectors. And if I set that equal to b, then that's just setting things equal to this vector, right? Is it clear how I can transform this system of linear equations into this matrix equation involving a matrix here, a vector x, and a vector b?
So wait, the m's, like if you have a subscript m, that represents like the number of rows, right?
Where do you see a subscript m? I should have written only n's.
Oh, only n's. Okay.
Where do you see an m?
I thought I saw an m like in that line, but I guess not.
Yeah, hopefully. So right now I'm only dealing with n by n systems or n by n matrices.
Oh, okay.
Or n by 1 vectors. Okay. Are we okay with this, about this translation?
Yes.
Great. So a solution to this linear system is a vector x such that ax is equal to b, right? That's what it means to find a solution to this linear system involving a and b. I want to find some vector x such that when I do the matrix multiplication, or in a different language, if I do the linear transformation on the vector x associated with a, I end up with the vector b. Is this okay?
Yeah.
Great. So as is now customary for us, if the vector b is equal to 0, then this is a homogeneous linear system. Okay, so in particular, what that means is if we're dealing with a homogeneous linear system, we're asking, is there a solution to ax is equal to 0. My claim is that no matter what a is, I can always find a solution to ax is equal to 0. Someone tell me what that should be?
Would it be x equals 0?
Yes, very good. We can always find a solution x is equal to 0 is always a solution. A way to think about this is that any linear transformation of vector spaces, here of course I'm drawing a linear transformation from a two-dimensional vector space to a two-dimensional vector space, but this is a rule that holds for any linear transformation of vector spaces. The rules that we had for linear transformations were that a sum of vectors has to be mapped to the sum of the images of the vectors, and scalar multiples have to be sent to scalar multiples. And what that means is that the 0 point of the first vector space V, 0 always has to map to 0, W. So in a linear transformation, zero must go to 0. The 0 vector must go to the 0 vector. And so what this is asking us is find some vector in V such that after I apply the linear transformation, I get to 0. Well, one answer will always be the 0 vector will always be sent to the 0 vector. There might be others, but at the very least, we can always find a solution, namely x is equal to 0. Very good. Okay. If we return now to the now let's return to the non-homogeneous case. Return to ax is equal to b. And here, again, we're going to assume that a is n by n. So I can really think of this as a linear transformation from a vector space to itself. So whether or not we can find solutions depends on a. In particular, can anyone guess a condition that I could ask of A such that I can always find a solution?
It's diagonal.
Diagonal will almost work. If it's diagonal with non-zero entries, then that will certainly work. The key thing that I want is I want for A to be invertible. If A is invertible, what does it mean that I have an invertible matrix? It essentially means that there exists a B such that, in this case, BA is equal to the identity. I haven't really told you about this, but if a pair of matrices is equal to the identity, then AB is equal to BA. So in this special case, when their product is equal to the identity, they commute. And I can call this A inverse. Call B equal to A inverse. And then I can manipulate things as I would an algebraic inverse. So if A is invertible, I can multiply both sides by A inverse. So in particular, I would get A inverse times A times X is equal to A inverse times B. What's A inverse times A?
Identity.
Yeah, exactly. So what is the identity matrix multiplied by the vector X?
Just x?
Exactly. The identity times X, which is equal to X, is equal to A inverse B. To A inverse B. So in other words, if the matrix A is invertible, then we can solve for x and get some expression, x being equal to A inverse B will precisely satisfy if I plug in this vector, which is a well-defined vector, in for x, then I'll get B back, of course, right? If I apply A to this vector, A inverse B, I'll certainly get back B. Is this okay?
Yeah.
Okay. So one thing to remember is if A is invertible, then we can always find solutions. And also this solution will be unique. Also, solution is unique. Okay? Namely, the only x that works is precisely A inverse of B. The situation changes when A is not invertible. And I can do an example of this. So if A is not invertible, then two things change. One, we may not be able to find a solution. A solution x to ax is equal to b, and b, if we are able to find a solution, it won't be unique. Okay, and I'm not going to prove either of these statements, but here I at least want for us to see how this works with our nicest example, which is the map R cross R, mapping to R cross R, right? This is a two-dimensional vector space mapping to a two-dimensional vector space, and it maps along the matrix 1, 0, 0, 0, or if I want to write it another way, this is the projection linear transformation, where I send, here's a vector E1 and here's a vector E2. I'm going to send the vector E1 to the vector E1, and I'm going to send the vector E2 to 0. Are we okay with, here's E1, here's E2, here's f of E2? Are we okay with the pictures that I've drawn here? And how all this ties together? How this matrix is the same as this linear transformation?
Yeah.
So here's an example. If I want to solve the equation 1, 0, 0, 0, x, I'll write it as a vector x1, x2, is equal to 1, 1. What I'm asking for is a vector over here with coordinates x1 and x2, such that when I map it over here, it goes to this point, 1, 1. Is there a solution to this equation, to this linear equation?
No.
No, there's no solution to this linear equation. No solution. Why is that?
Because we know that you can't map to something that's off the x-axis.
Exactly. Every single vector in here gets mapped to something on the x-axis. So I can't hit something that's off of the x-axis. So here we see the moment that our linear transformation becomes singular, or our matrix has determinant 0, there are vectors that can't be hit. Or in other words, there are vectors B with no solution AX is equal to B. So this is the first bullet. The second bullet, the second point, is let's find a vector which does have a solution. So 1, 0, 0, 0, x1, x2 being equal to, let's say, -2, 0. So here I'm looking for vectors which are mapped to the coordinate -2, 0. First of all, are there solutions to this linear equation?
Yes.
Yeah, what's one solution?
X1 equals -2.
Yeah, I know that the vector -2, 0 will map to the vector -2, 0. So here we have solutions. But we actually have infinitely many solutions. The solutions that we have can be written as -2, alpha, where alpha is anything, right? Because if I do the matrix multiplication, -2, alpha, multiplied by this matrix, I get back exactly -2 times 1 plus 0 times alpha. And then down here, I get -2 times 0 plus 0 times alpha, which is exactly equal to -2, 0. So, oh, you can't see. So this means for any coordinate alpha I put in here, I will end up with a solution because this matrix maps any vector of this form to this vector. A way that is suggestive to write this is I could write the solutions as -2 times E1 plus alpha times E2. Right, this is the same thing as -2, 1, 0 plus alpha times 0, 1. So this is just rewriting what I had here. But now it becomes clear what the linear transformation does to this vector. Remember, the linear transformation, f of -2 E1 plus alpha E2, what is a rule about linear transformations? The linear transformation of a sum is equal to
the linear transformation of its parts.
Yes, exactly. The sum of the images. So this is equal to f of -2 E1 plus f of alpha E2. What's our next rule about linear transformations when I'm dealing with scalar multiples?
You can like factor it out, kind of.
I can pull out scalar multiples. So this is the same thing as -2 times f of E1 plus alpha times f of E2. And now you see I've told you exactly what f does to E1. It sends it to E1. And I've told you exactly what f does to E2. It sends it to 0. So this is just going to be exactly -2 times E1. In other words, the whole line, like all of the vectors in this line, all can be written as -2 times E1 plus some constant times E2. And this linear map sends E2 to 0, or in other words, it collapses this whole line onto this point. And when I'm writing this collection of solutions, this infinite family of solutions, I'm exactly stating the property that this whole line gets collapsed onto -2, 0. All I really, if this is a little confusing, that's, I apologize. But the real point that I want to draw out is that the moment that A is not invertible, then we might not have solutions. And if we do have solutions, they're not unique. We generally have a whole collection of solutions. And you can think about that collection of solutions as being parameterized by vectors that get sent to 0. So since E2 gets sent to 0, I can add on any scalar multiple of E2, and that won't change the image of the vector. Is this okay? Any questions?
No, that sounds good.
Great, thank you. Okay, so with that gone, or with that understood, then let's talk about solving linear systems. And this, what I'm about to discuss, should be familiar to you. This is just called Gaussian elimination. And more or less, this corresponds to the elimination method of solving linear systems. What we're going to do is we're going to write down a particular linear system. So I'm going to do an example. X1 minus 2x2 plus 3x3 is equal to 7. Negative x1 plus x2 minus 2x3 is equal to negative 5. And then 2x1 minus x2 minus x3 is equal to 4. So this is some linear equation or linear system. And I'm going to be able to write this in our matrix notation as first I write a linear or a matrix associated with this collection of linear equations. And I'm just going to pick off the coefficients to get my matrix. So in particular, this should be 1, negative 2, 3, negative 1, 1, negative 2, and 2, negative 1, negative 1, x1, x2, x3 being equal to the vector 7, negative 5, and 4. Right? I've translated this linear system into my concise form ax is equal to b. And I'm wondering if this has a solution and what are the solutions if they exist. We all right with this?
Looks good.
What's the first thing that we should check?
See if A is invertible.
Yes, we should check if A is invertible, because if it's invertible, we immediately gain the information that yes, there's a solution, and B, it's unique. So what is the determinant here? Let's do cofactor expansion, but let's not expand along the first row. Let's expand along a different row just so that we can see what changes. So can someone tell me either a row or a column to expand along?
The bottom one.
Okay, let's expand along the bottom row. So here, the coordinate here is 3, 1, which means that I'm going to start off with a positive. So I'm going to do 2 times the determinant of the cofactor. So I delete these rows and I get determinant of negative 2, 3, 1, and negative 2. Then I do negative 1, so plus negative 1 times negative 1. This negative 1 comes from the fact that I'm at the 3, 2 entry. This negative 1 just comes from the entry itself. And now I do the determinant of the cofactor times det of 1, 3, negative 1, negative 2. Then plus 1 times the entry, negative 1, times the determinant of 1, 1, negative 2, negative 1. Are we comfortable with this procedure of doing cofactor expansion to find the determinant of this matrix.
Mark,
Mhm.
I know you went over this before, but can you explain again why we need to have that minus sign in front of the second one?
Yes, maybe I'll explain it in the following way.
Okay.
In a 3x3 matrix, here is position A11, here is A21, here's A31, here's A12, here's A22, here's A32, here's A13, here's A23, and here's A33. To this, I'm going to associate the following matrix of either ones or negative ones, and I'm going to put a 1 or a negative 1 depending on whether the sum of these is even or odd. So 1 plus 1 is even, so I get a 1 here. 2 plus 1 is odd, so I put a negative 1 here. 3 plus 1 is even, so I get a, so I'm going to get a checkerboard like this. And this tells you the coefficients of plus or minus 1 as you expand along cofactors. So you're most used to expanding along the top row, and then this is where you get your positive, negative, positive. But if you expand along the second row, you're going to have a negative, positive, negative. And similarly, if you expand along the middle column, you're going to also do negative, positive, negative. Whereas if you expand along the first column, you'll do positive, negative, positive.
And regardless of which row I choose, row or column, I should derive the same answer.
Yes, all the answers will be the same. That's correct.
That makes sense. All right, thank you.
Yeah, so maybe think of this checkerboard. And this holds for any m by m matrix, right? It's just you always start with 1 in the upper left corner, because that's always entry 1, 1, and then you checkerboard out. This is one easy way to remember what's going on. Obviously, I didn't explain why this holds. I'm just giving you the rule.
Why did you decide to expand along the bottom row? Like, is there any benefit towards using any single row at a given point?
In this case, there's no benefit. There is a benefit if one row or column has lots of zeros, because then a lot of the calculations just simplify because you're doing 0 times some determinant.
Gotcha.
So
Okay.
if these negative ones were both zeros, then it would be definitely better to expand along the bottom row. Since there are no zeros anywhere here, all of the computations are going to be at approximately the same level of computation.
That makes sense. Thank
But
you.
anytime that you've got a bunch of zeros appearing in a row or column, you should expand along that row or column for sure, just to simplify your life. Okay, so in particular, if we actually do this computation, this is going to be 2 times this determinant, which is 4 minus 3, which is 1, plus a negative 1 times a negative 1, so a 1 times the determinant. This is negative 2 minus a negative 3. Negative 2 minus a negative 3, so negative 2 plus 3. This is a 1. And then this last one is plus negative 1 times the determinant here, which is 1 minus 2. So minus 2. So this gives me a 2 plus 1 plus 2, which is equal to 5, as long as I did this correctly. So what this tells me, since the determinant is not equal to 0, what does that tell me about solutions to this linear system?
It exists and it's unique.
Exactly. There exists a unique vector x satisfying ax is equal to 7, negative 5, 4. Okay, so this is just to remember, this is just to use these things that we just discussed, namely when do solutions exist, when are they unique. It's easy when A is invertible. How do we actually find the solution? So actually finding the solution is Gaussian elimination. And what I'm going to do is I'm going to write this out. I'm going to take a new page and write this out as, I'm going to write out just the matrix that I have for A. So that's negative 1, sorry, not negative 1. That's 1, negative 2, 3. -1, 1, -2, 2, -1, -1. And then I'm going to put in the vector that it's supposed to be equal to over here. So this is called an augmented matrix. Here I'm going to have a 7, a -5, and then a 4. And now I'm going to do my elementary row operations. Which say that I can switch the order of rows, switch rows. I can multiply rows by constants. And I can add scaled copies of rows to each other. And my goal is to make A upper triangular. Technically upper triangular with 1s along the main diagonal, but this is a method for solving a linear equation. So does anyone, and I need to keep track of what all my row operations do to this vector that I'm supposed to be equal to at the end. So the first thing that I want to do is, since I already have a 1 up here, I'm going to replace column 2 by the sum of column 1 and column 2. And I'm going to replace column 3, well, I'm going to multiply column 3 by a -1, and then I'm going to add 2 times this row. Is anyone uncomfortable with all these words that I'm saying or what I'm about to do?
Yeah, kind of.
Yeah, I don't get it.
Okay. Then I'll go slowly. So what I want is I want to use these row operations to get a matrix which looks like 1 and something and something, a 1 and something, and then a 1. And then whatever I have going on here. And then I'll be able to read off the solution, because the solution will be x3 has to be whatever appears here. Since I already know from here what x3 has to be, I can solve for x2, because this will become a linear equation where I know one of the unknowns. And then lastly, I'll be able to solve up here. So my goal is to upper triangularize the matrix A. Let me show you what I'm going to do in each step. Here, I'm going to add row, or replace row 2 with row 1 plus row 2. This is essentially the third thing that I'm allowed to do. I can replace a row with a linear combination of rows. So the new augmented matrix that I get when I keep the first row the same, 1, -2, 3, and 7. I keep the third row the same, 2, -1, -1, 4. But I replace the middle row with the sum of these two rows. So what's the sum of these two rows coordinate-wise?
0, -1, 1, and 2.
2. Is this okay?
Yeah.
And my guess is that you're familiar with doing this if I wrote down x1 minus 2x2 plus 3x3 is equal to 7, and negative x1 plus x2 minus 2x3 is equal to -5. Are you familiar with the idea of trying to eliminate variables?
Yeah,
Like if I add these two equations together, I'll get negative x2 plus x3 is equal to 2. Is this okay? Maybe what I was talking about here seemed foreign, but is this notion of eliminating variables at least something you've seen before?
Yeah, now it makes
Yeah.
sense.
Okay. Yeah, this is kind of the formal way to approach this, but what I'm actually doing mathematically is something that I believe you've seen before.
I think it just sounded like a lot of words. so-
Yeah, that was my fault. But for those who are uncomfortable with the words that I said, are you okay with this step?
Yeah, thank you.
Yep. And then I'm going to do the same thing with the first and the third row. What I want is I want to have a 1 up here, and I want to have zeros below it. So I want to replace the third row with some linear combination such that I get a 0 here. So what I do here is multiply, or I'm going to replace row 3 with -2 row 3 plus 2 row 1. If I do -2 times, or sorry, -1 times row 3 plus 2 times row 1, so that's going to make this first coordinate -2, and this will make the first coordinate 2. So when I add them, I'll get a 0 here. And what I get then is I'm going to leave the middle row alone. I get a 1, -2, 3, and 7. Here I get a 0, -1, 1, and 2. What do I get when I do this operation here? Well, I know that I get a 0 here. I get a -1 times this plus this. So I get a 1 plus a -2. I get a -1 out here. Then I do a -1 times this, which is 1. Wait, sorry, this is a lie. I need to do a -1 times this plus 2 times this. In other words, in this coordinate, I get a 1 plus -4. So I should get a -3 here. Do we agree? Negative times this plus 2 times this.
Yeah.
Then the last one, I do negative of this plus 2 times this, so I get a 7. And then do a negative of this plus 2 times this, so -4 plus 14 is 10. We okay?
Yes.
It looks like I'm very close to having a next step done. This row is almost of the form 1 something something. I just need to multiply by,
-1.
yeah. Row 2 becomes negative row 2. So then I get 1, -2, 3, 1, -1, this is a 7, -2, and then I keep this one the same, 0, -3, 7, 10. I'm almost upper triangularized. What's the next thing that I need to do?
Divide row 3 by 7.
Well, before I do that, I need to get rid of this -3, right? I want a 0 down here.
Right, right.
So what I'm going to do is I'm going to replace row 3 with row 3 plus 3 times row 2. Row 3 goes to row 3 plus 3 times row 2. So then I'm going to get 7. The first 2 rows stay the same. 1, -2, 3, 0, 1, -1, -2. But now I'm going to have a 0 here. I'm going to have a 0 here because that's exactly the way that I planned it. And then I get a row 3 plus 3 row 2. So that's a 7 plus -3, which would be 4. And then a row 3 plus 3 row 2 is going to give me a 4 over here as well, right? Because it's going to be a 10 plus -6. We okay with this?
Yeah,
What's the last thing that I need to do to get it upper triangular?
divide the bottom row by 4.
Exactly. Row 4 maps to 1/4 of row 4, or row 3 goes to 1/4 of row 3. And so what I'm left with in the end is 1, -2, 3, 7 0, 1, -1, -2, and 0, 0, 1, 1. What does this last equation translate to if I go back to the variables x world?
x3 equals to 1.
Yes, this is the same thing as x3 is equal to 1. What's this equation?
x2 minus x3 equals to -2.
Very good. And what about this one?
x1 minus 2x2 plus 3x equals 7.
And now you see what I've done with this procedure is made it almost instantaneous for how I solve it. x3 has to be 1. If x2 minus 1 is equal to -2, then what does x2 have to be?
-1.
1, -1. And then if I have x1 minus 2 times -1 plus 3 times 1 being equal to 7, that's the same thing as 3 plus 2 plus x1 is equal to 7, and I get
2.
2. So once I have upper triangularized my matrix, it is pretty much immediate what the vector x should be, such that when I plug in this x, I get back b. This is the unique solution. Ax is equal to b.
Okay, so I understand the procedure, but it seems like when I look at this, my instinct is not to do this. I feel like if I just solved it using the x, I would be able to derive the same answer.
You mean if you just started with this equation, well, where is
Yeah,
it?
like
You
if I
just started with
used
this
the
and just
three
started.
equations, that I could manipulate it in a similar manner just without using a matrix. So I don't fully understand the purpose of this.
So so you're absolutely correct. Generally, there are two ways to solve a linear system that you get written out like this. One is the substitution method, and the other is the elimination of variables method. And you're correct. You can absolutely solve these linear systems without using these matrix methods. All that I'm doing here is showing you how the mathematical idea of elimination of variables works in the context of a matrix. So this makes it very algorithmic.
Yeah.
There are like this makes it plain at each step what you must do to upper triangularize. Like this takes away any judgment that you have to make about substituting things in for your equation or things like that. You're absolutely right that there's no new mathematical content. This is just, first of all, showing you what this looks like in matrix notation, and B, making it very kind of algorithmic.
Okay.
Any questions here? It is already 12:18. It is unbelievable how fast the time is going by. What do I want to say here? So Gaussian elimination also works if A is singular. In other words, here, A was invertible, so we knew that there existed a unique solution, and Gaussian elimination brought us to that unique solution. If your matrix is singular or not invertible, you can also find all the information, namely under what conditions you can produce a solution and what the general form of the solution is. That can also be done via Gaussian elimination. just that I have little time, but I think I need to do this. So here's what I'm going to do. We're just going to go for it. So let's consider the following system. X1 minus 2x2 plus 3x3 is equal to b1. Negative x1 plus x2 minus 2x3 is equal to b2. And 2x1 minus x2 plus 3x3 is equal to b3. So this becomes the system just in matrices. It's going to be 1, negative 2, 3, negative 1, 1, negative 2, 2, negative 1, 3. And then the augmented matrix is b1, b2, b3. I wanted to do this whole calculation and actually, first of all, compute the determinant of this matrix, and then make sure that we go through and do what the Gaussian elimination tells us to do. But I don't think that I have quite enough time for that here. So I urge you, this is an example in the book. This is example somewhere in 7.3, and I really urge you to go over this example carefully on your own time, just because I need to move past this. So one point is that A is singular, which means if we compute the determinant of this matrix, we'll get 0. So already we expect that only certain vectors B have a solution, AX is equal to B. And second of all, we don't expect the solution to be unique. In fact, what you get if you try to upper triangularize this matrix, or in other words, if you try to do Gaussian elimination, just as we did on the last page, and this is what I don't feel I have time for right now, you'll get the following. You'll get 1, negative 2, 3. You'll get 0, 1, negative 1, and then you'll get 0, 0, 0. This is going to be equal to b1 and negative b1 minus b2 and b1 plus 3b2 plus b3. So here's the first thing to point out is when we have done our process of trying to upper triangularize this matrix, this last coordinate totally vanished, right? There's all zeros here. I couldn't get a 1 to appear here. In other words, I had like 2 vectors here, and when I added or subtracted the linear combination to make this thing 0, this thing also became 0. That's okay. This is going to happen if you start off with a singular matrix. If I write back out in coordinates what this means, this is expressing 0x1 plus 0x2 plus 0x3 is equal to b1 plus 3b2 plus b3. This is expressing a condition on the vector B such that AX is equal to B has a solution. This last row is telling me if I want a solution for AX is equal to B, then I have to have B1 plus 3B2 plus B3 is equal to 0. If I find some vector that does not satisfy this, there is no solution. So for instance, the vector B is equal to 1, 1, 1 has no vector X such that A sends x to B because 1 plus 3 plus 1 is not equal to 0.
This is a little off topic.
Sure.
I mean, same thing, but this is the same as saying that x3 is free, right?
You can choose x3 to be free. That's correct. That's one way to think about it. You could choose other things to be free, but in this case, one way of thinking about this is saying x3 may be allowed to be free.
Okay.
And then if you want to find solutions, one thing that we can do is exactly what was just suggested. We let x3 be some number, be arbitrary. So we're just going to call x3 equal to alpha. And then we can go through and solve all of these things. So if x3 is equal to alpha, first we need to pick some vector that satisfies these things. So let's do an example. Can someone think of 3 numbers such that the first number plus 3 times the second number plus the third number is equal to 0?
Like 1 minus 1 and 2.
1 minus 1 and 2. Very good. So let's pick B is equal to 1 minus 1 and 2. Then 1 minus 3 plus 2 will be 0. So AX is equal to B has solutions X. Okay. So as suggested, we can let x3 be free. So we're going to let x3 be equal to alpha, where alpha I think of as a variable. Alpha could be whatever. Then I write down the next parts of my matrix. Here, this equation says x2 minus x3 is equal to negative b1 minus b2. In our choice, that means negative 1 minus negative 1, which is equal to 2. So this shakes out to be x2 minus alpha is equal to 2. So thus far, my solution looks like x3 is equal to alpha, x2 is equal to 2 plus alpha, and then lastly, this top condition says x1 plus x2, sorry, minus x2, minus 2x2, plus 3x3 is equal to b1. In our case, that's 1. But I already know what x3 and x2 are, so I get x1 plus negative 2 times 2 plus alpha plus 3 times alpha is equal to 1. And here I get x1, let's see, this is going to be minus 4 minus 2 alpha plus 3 alpha is equal to 1, or x1 is equal to 1 minus alpha, and then plus 4 is going to be 5. This is just what I got by moving all the alphas and numbers over to this side. So in the final count, what I get is that the solution x is 5 minus alpha, 2 plus alpha, and alpha for any alpha. In particular, we don't just get one solution, we get a whole family of solutions parameterized by alpha. If I plug in alpha is equal to 0, I'll get a solution. So A times 5 minus alpha, 2 plus alpha, and alpha will be equal to 1, negative 1, and 2 for any alpha. I have a feeling like I just went way too fast and that a lot of people are confused by this, and I want to try to help in hopefully not too much time. Yikes. Does anyone have questions?
I have
Yeah.
a question.
So why did you choose X3 to be alpha and not any of the other ones to be alpha?
Just because that's essentially just a choice that I am able to make. So if I chose something else to be alpha, things would also work out. It's just more easy computationally if I choose the last coordinate to be alpha.
On the line there, x2 minus x3 equals -1 minus -1.
Yep.
Shouldn't that be 0, not 2?
Oh, shoot. You make a good point. So really what this should be is x2 minus x3 is equal to 0. So this means that x2 is equal to x3, in which case this should also be alpha. And then I need to go back and change this. So then I'd get x1 minus 2 alpha plus 3 alpha is equal to 1. So x1 is equal to 1 minus alpha. So that changes all my stuff up. So I made an error in the calculations. I think it should be 1 minus alpha, alpha, and alpha. Sorry about that. All that has happened here is that I am solving this systems of equations, but I'll be able to find a solution for any alpha equal to x3, and then I just plug in x3 is equal to alpha and write x2 in terms of a number in alpha, and then plug in whatever I got for x2 and x3 back into my original equation and get something in terms of alpha as well. So essentially now I just expect alphas to be floating around in my solutions, and this is due to the fact that I should have a whole family of solutions.
I had a question.
Sure.
Why do we have that x1 minus 2x2 plus 3x3 equals 1?
So first what we did is we picked a vector that satisfied this condition. So from our work to upper triangularize this matrix or this augmented matrix, I found out that I only have solutions if this condition is satisfied.
Right.
So then we picked some random vector such that this condition is satisfied. So we know that ax plus b, where b is this, has solutions.
Mm-hmm.
And now you're asking me why I got, so can you repeat your question again?
No, I was just wondering, like, I got 0 for that. I might be making a computational error, but I was just like, because we picked it to be 0.
We picked what to be 0?
Like the expression.
So we know that we have to have b1 plus 3b2 plus b3 being equal to 0.
Right.
So what I'm kind of interested in is I'm interested in vectors b which are not 0, such that they still satisfy this.
Okay, thank you.
Yeah. Okay. I definitely recommend that you take some time on your own to try to understand this phenomenon on the homework, and so you can understand how we use Gaussian elimination to try to find the families of solutions to ax is equal to b when a is singular. May I continue?
Yeah.
Maybe I should do a really simple 2x2 example first. That might be better, actually. So you can see really quick what this looks like. So let's say that I take a singular matrix, And I'm going to do 1, 1, 1, 1. X1, X2 is equal to B1, B2. So this has determinant 0. So A is singular, right? So the first thing that I want to do is I want to find for which B1 and B2 do I get solutions. So when, for which B do we get solutions? And the answer is, let's upper triangularize this thing. So we have 1, 1, 1, 1, and then B1 and B2. This row is fine because I've got a 1 out front, and now I want a 0 below it. So what do I need to do to this augmented matrix to get a 0 below this 1?
You can take row, like assign to row 2 minus row 1.
That's right. I can assign here, I'll do probably negative row 2 plus row 1, but either way would work. So what I get here is 1, 1, and B1, and now row 2 goes to row 1 minus row 2. So I do 1 minus 1 is 0. 1 minus 1 is 0. B1 minus B2. Okay? So now I have upper triangularized, but one of my rows has no 1 in it. It's just 0. So this last line tells me x1 or 0x1 plus 0x2 is equal to b1 minus b2, or in other words, b1 minus b2 has to be equal to 0. This is the condition on the vector b so that I get solutions. To A, x1, x2 is equal to b. b1 minus b2 being equal to 0 means that what do these vectors look like?
B1 equals B2.
Right. So b1 has to be equal to b2 in order for me to get solutions to this. Can someone pick for me some vector such that b1 is equal to b2?
2, 2.
Great. Now let's solve 1, 1, 1, 1 times x1, x2. Well, I don't want to go all the way back up here. I'm going to go here. 1, 1, 0, 0. And then what I want, and I'm going to plug in, b is equal to 2, 2. So in other words, b1 is equal to 2, and b1 minus b2 is equal to 0. So this is the equation, x1 plus x2 is equal to 2. This thing down here, this row of zeros, tells me x2 is free. So I'm going to set x2 equal to alpha. And then here I'm going to have x1 plus alpha is equal to 2. Or in other words, the solution is 2 minus alpha and alpha. The matrix 1, 1, 1, 1 will always send 2 minus alpha comma alpha to 2, 2. And we can just literally check this. 1, 1, 1, 1. How does this act on the vector 2 minus alpha and alpha? Well, the first column is going to be, or the first entry is 2 minus alpha plus alpha. And the second entry is 2 minus alpha plus alpha, which is equal to 2, 2. So this is a whole family of solutions for any alpha that I pick. Alpha could be 1, alpha could be 5, alpha could be 5, alpha could be pi. Any alpha, this matrix will send this vector to 2, 2. With the 2 by 2 example, it's faster to do every step, and you can kind of see what's going on here. The last thing that I should do is draw a picture. What does the matrix 1, 1, 1, 1 do to the vectors E1 is equal to 1, 0, and E2 is equal to 0, 1? Where does E1 get sent to?
One, one.
1, 1. Where does the vector E2 get sent to?
Also one, one.
Also 1, 1. This is f of E1. This is also equal to f of E2. Now, geometrically, you see this condition that we found that B1 has to be equal to B2 is saying the only things that are hit under this linear transformation are the things lying on this line, because this linear transformation 1, 1, 1, 1 sends all the vectors onto this line. If I want to find the thing that hits 2, 2 in particular, then it's going to be anything along the coordinates 2 minus alpha, alpha. So this is something like this line. This line gets mapped to this line.
So you said
Okay.
that
Yes?
you said that the bottom line of the matrix is what told you that x2 was free.
Yes.
So we can make x1 free if we wanted, right?
Yeah, x1 could be just as free, absolutely. And you can see that from this equation. The only equation that I'm solving is x1 plus x2 is equal to 2. Either I let x2 be equal to alpha, and then I say x1 is equal to 2 minus alpha, or I let x1 be equal to alpha, and then I say, well, x2 is just 2 minus alpha. Either way, it works.
Okay, so in order for that to work, all of the terms at the bottom half of the matrix would have to be 0, right? Or no, not necessarily, because you could have, like, okay, what if the bottom row read 0, 1, 0? What would be different?
0, 1, 0?
Yeah.
Then this actually corresponds to a non-singular matrix. The whole behavior will change, because now if I got this in the Gaussian elimination, this tells me, first of all, there exists a solution no matter what B is. B, that solution is unique. And now, instead of this one equation, I have two equations. I have x1 plus x2 is equal to 2, and also x2 is equal to 0.
Right.
So it adds in this extra condition on the vector x in order to be a solution.
Okay, I think that makes sense.
So that changes things drastically, actually. Okay, I didn't intend to spend that time, but I think that was valuable and important. Do you agree? Is it helpful to see the 2 by 2 case?
Yeah.
Okay, thank you. I'm happy to hear that. I'm nervous about how to spend my time as we continue. Okay, this is the last purely matrix thing that we're going to do. Eigenvalues and eigenvectors. So when we write AX is equal to Y, then we think of this as finding a vector X such that the matrix A, or the linear transformation A, transforms this vector X into the vector Y. It turns out we can get a huge amount of information, lots of info about A by finding out if there exist any vectors that A sends to a multiple of themselves. Right? So these linear transformations are pretty complicated, but as I mentioned to you, you should more or less think of them as sending lines to lines, and maybe sending some lines to zero, and what that implies, right? So what we're asking here is, for a given linear transformation A, can I find a line that is sent to itself? It's sent, right? So a line should be sent either to a line or to zero. Is there a line that is sent back onto that same line? Is it clear what I'm asking for here? Is this okay?
Maybe an example would help.
Sure. Let's do the example of the matrix 1, 1, 1, 0. This is a particularly simple example. What this does, let's examine what this does to E1, which is the vector 1, 0. What does this do to E1? Or actually, let me do -1 here. -1, 1, 1. What happens to E1? Well, -1, 1, 0, 1. I just multiply 1, 0, and I get that this is equal to, what's the first coordinate?
-1.
What's the second coordinate?
0.
What's the relationship between 1, 0 and -1, 0?
Just a negative.
Exactly. Here, E1 has been sent to -E1. How about E2? Where is E2 sent? First coordinate is
1.
second coordinate is
1.
E1 was sent to a multiple of E1, but E2 was sent to E1 plus E2. E1 is what's called an eigenvector, and E2 is an eigenvalue. Or no, sorry, E2 is not an eigenvector. Because E1 is a vector that was sent to a scalar multiple of itself, but E2 was not sent to a scalar multiple of itself. Any questions here?
I think you're good.
Okay. So now what I'm going to do is I'm going to write down the equation for, so let's write down, so I don't know if I defined it. Definition, an eigenvector for A is a vector such that AV is equal to lambda V for some lambda, right? This is exactly what it means for a vector to be sent by A to a new vector, which is a scalar multiple of what we started with, where lambda is something in the field, either R or C. We agree that this equation is exactly what I'm talking to you about. This means that the linear transformation A has sent the vector v to a linear multiple of the vector v, or scalar multiple of v?
Yes.
Okay. This can be rewritten as AV minus lambda v is equal to 0. And this can be rewritten as A minus identity times lambda times v is equal to 0. I should point out another piece of definition. Lambda is called the eigenvalue of v. So this thing is telling me that AV is equal to lambda v. But if I just subtract this vector over here, this is telling me that AV minus lambda v is equal to 0. And for any vector, I can write a scalar multiple of v by the identity matrix times the number lambda times the vector v, right? Like if I have a vector v1 and v2, and I want to get the vector, say 3v1 and 3v2, I can do this by just multiplying 3, 0, 0, 3, which is equal to 3 times identity times v1, v2, right? This is going to be equal to 3v1 and 3v2. So multiplying a vector by a scalar can also be accomplished by matrix multiplication, where I take a number times the identity matrix, and then I matrix multiply, and I get 3v1, v2. Is this okay? Are we okay with the passage from this expression to this one?
Yeah.
Any questions? Is that a no? Are we okay?
Yeah, we're good.
Okay. Now, there's kind of an obvious solution for an eigenvector. What vector is always an eigenvector?
Zero?
Yes, 0 is always an eigenvector because any linear transformation sends 0 to 0, which, if you want to be pedantic, is a scalar multiple of 0, right? So 0 is always an eigenvector. What is the condition on a matrix such that it sends other vectors to 0, such that the solution AX is equal to 0 is not unique?
When the determinant of A is 0?
Exactly. AX is equal to 0 has more than just X is equal to 0 as a solution, precisely when A is singular. Or in other words, that A is equal to 0. Is this okay? Any questions?
Precisely when mean the same thing as if and only if?
Yes, if and only if. So, if we're after eigenvectors, namely we're after v's, such that v is sent to lambda v, that's the same thing as finding v's such that A minus identity times lambda sends v to 0. What do we require of this matrix in order for it to send some non-zero vector to 0? By what we just discussed here.
Its determinant is 0.
Yes. In order for AV is equal to lambda v to be satisfied, we must have A minus lambda times identity be singular. And by this, satisfied for non-zero v. So in other words, if I want the eigenvectors, but actually what are more accessible and what I can find first are eigenvalues. The lambdas are easier to find than the v's. And the way that I find the lambdas, the eigenvalues, is I look at when this matrix, A minus the identity times lambda, is singular. So let's do some examples. Find the eigenvalues of this matrix. 3, -1, 4, -2. So this is A. Okay. What I want to find lambda such that A minus lambda times identity is singular. A minus lambda times identity is equal to, in this case, 3 minus 1, 4 minus 2, minus lambda times 1, 1, 0, 0, which is equal to 3 minus lambda, -1, 4, -2, minus lambda. So the thing that you should remember is, when trying to find the eigenvalues of A, subtract lambda from all the diagonal terms, and then compute the determinant of this. So what is det of A minus lambda times identity in this case?
Lambda squared.
Well, I'll just write it out. 3 minus lambda times -2 minus lambda minus -1 times 4, right? Is it okay what I'm doing here? Do you agree that this is the determinant of this matrix?
Yeah.
Okay, well, this is just going to be a nice polynomial, right? If I FOIL out, I get -6 plus lambda minus 3 lambda plus lambda squared plus 4. And this turns out to be equal to
You get plus 2 lambda
plus 2 lambda?
instead of just plus 1.
Oh yeah, plus 2 lambda, thank you. So what I get is lambda squared plus lambda minus 2. This is the determinant of A minus lambda.
So we get 2 values for lambda then?
Yes, we expect 2 eigenvalues associated to a 2 by 2 matrix. Of course, they might be repeated, right? This is a polynomial. I just want to now find the roots. What are the roots of this polynomial?
-1 and 2.
Yeah, lambda minus 1, lambda minus 2. So what are the eigenvalues of this matrix?
That should be a +1.
1 and 2. Wait, oh, plus over here?
On the 1.
I think I like this, right?
Oh, yeah, right. Sorry.
So 1 and -2. These are the eigenvalues.
Wouldn't it be lambda squared minus lambda?
Oh, yeah, you're right. And if it's minus lambda, then this changes to +1 and -2.
Yeah.
And so then my eigenvalues are -1 and 2. Okay, it's 1. I know that today was very fast and probably too much. So let me try to summarize briefly what I want you to digest from today. First of all, AX equals B exists unique solution if A invertible if A singular may not have solutions, or not all B have solutions. If B has a solution, it's not unique. So this is some basic idea about when you can solve linear systems. The second thing that I want you to remember is Gaussian elimination. So you should practice finding the solutions to linear equations using Gaussian elimination. I did 3 examples, one where A is not singular, and then 2 examples where A is singular. And you notice that when A was not singular, or A was invertible, we got the unique vector x that worked. When A was singular, in both cases, we got a family of vectors parameterized by alpha, such that that whole family of vectors was mapped to our given B. Gaussian elimination is the second piece. And the third piece is the eigenvalues of A are the roots of the polynomial det A minus lambda times identity. You're going to need to compute this polynomial often. So just kind of have it ingrained in your head that to compute the eigenvalues of a matrix, you take that square matrix, you subtract lambda from all the diagonal terms, you take determinant, and then you find the roots of that polynomial that you got. That's how we find eigenvalues. Or yeah, eigenvalues. These are the 3 main things that I hope that you take away from today. Any questions?
Yeah, what's like the special property of an eigenvalue again? It's just like you talked about it at the beginning. It's like it can transfer like a line onto itself.
Right, so the idea is you should think of linear transformations as sending lines to lines. If you have a line, and the question about eigenvalues and eigenvectors is, can we find lines that are sent to themselves by the linear transformation? Is that okay?
Okay, that makes sense.
And studying when is a line sent to itself, or when is a vector sent to a scalar multiple of a vector, led us to see, well, whenever that happens, A minus lambda times the identity has to be singular. How do we check when it's singular? By taking the determinant of this matrix and then finding the roots.
Okay, gotcha.
I know that I have just pushed a lot of material on y'all, so that's my fault for messing up the pacing of this course a little earlier on, but that's okay. Any questions?
Oh, I had a question about the homeworks.
Sure.
Are you going to be assigning any more homework?
Yes, I'm going to be assigning homework today on this material, which is 7.3. And I'm also going to be assigning homework on whatever I give you on Monday. It's unfortunate, and if you want, I can drop the grade for the last homework that I give you on Monday, but I want to give you practice problems for using, like, we haven't even seen how to use this stuff to solve first order linear systems of differential equations, right?
Right.
So what I will cover on Monday is how to use this matrix machinery to solve the most simple sorts of first order linear systems of equations. And then I want to give you homework so that you have a chance to practice that.
Okay, thank you.
I know that it's jammed up right against the final, and I'm sorry about that. But I do need to at least have you able to solve the most simple of those linear systems of differential equations. And we're very close. Once you're comfortable with finding eigenvectors and eigenvalues, then that's really all that you need to do. Like that'll give it to you. So we're close to being able to apply this to differential equations. It's just there's a lot of linear algebra that we need to build up first. Linear algebra should absolutely be a prerequisite to this class, and they're changing it so that it is. Yeah, I apologize that you've had to digest a large amount of linear algebra in a short amount of time. And this is not the best way to learn linear algebra, so I'm sorry for that. Any last questions?
Is final next Wednesday?
Yes.
What time is it?
If you're in a nearby time zone, that is, you're on the Atlantic time zone or in the United States, more or less, then it'll be 3 hours starting at 11:30, so starting at class time. If you're in a very far away time zone, then I'll make adjustments so that you don't have to take this at midnight or whatever.
Okay, thank you.
All right. If anyone wants office hours, I'll be back in like 10 minutes or 5 minutes, I guess. I'll be back in a couple minutes. Thanks for bearing with me on this lecture. Thank you for your questions, and sorry that this happened so quickly.